Good day, everyone. Today we are going to discuss our project titled The Wonders of Grundy's Game. In this video, we will focus on providing and explaining the mathematical concepts behind Grundy's game, which will mainly revolve around the Sprague-Grundy theorem. First, let's talk about Grundy's game. This game is an impartial combinatorial game played by two players. Impartial, as defined by Wolfram Math World, is a game in which the possible moves are the same for each player in any position. The aim of the game is to keep splitting the chocolates into unequal heaps, such as splitting 6 into 1 and 5, or 2 and 4, until all heaps are of size 2 or 1. The winner will be the one who makes the last move. Now, let us go through an example of playing the game of 5 chocolates. From here, we can see that the heap can be split into either 1 and 4 or 2 and 3. 1 and 4 can be further split into 1, 1 and 3. Thereafter, 1, 1, 2 and 1, while 2 and 3 can be further split into 2, 2 and 1.
These are the possible game stages that can happen according to what the player chooses to do. By definition, the winning position of a game, which is also a terminal position, has a number of 0. Let's focus on the left branch first. Let's look at the third game stage. The number of a game position can be found using the minimum excluded value, or MEX, which is the smallest non-negative integer not included in a set of integers. In this case, the number of the nth game stage is the MEX of the set of numbers belonging to the n plus 1th game stage. For game stage 4, the set of numbers for the game stage is 0. Therefore, game stage 3's number is MEX 0, which is equals to 1. Thereafter, game stage 2's number is the MEX of the set of numbers of the third game stage. Hence, for this game stage, its number is 0. Now, let's focus on the right branch. At the second game stage, its number is simply the MEX of 0. Combining both branches of the tree, we can finally see that the number of this game stage will be MEX 0 and 1, which is 2. With this method, we can conclude that the number of 5 is 2. We can use this method to calculate the numbers of any size of initial heaps of chocolates.
However, what if we are now dealing with larger initial heap sizes? Say for a chocolate bar of 15 segments. Are you seriously going to be doing this every single time?
I need the toilet. Start pain. Can. In this case, we can make use of the bitwise number XOR addition. Let's go back to the example we had just done for an initial heap size of 5. We calculate the number once again, using the max of numbers belonging to the second game stage, 1 plus 4 and 2 plus 3. But how do we calculate the number of the second game stage? Using the bitwise XOR addition. Rules of the bitwise XOR addition are as follows. 1 plus 1 and 0 plus 0 equals to 0. 1 plus 0 and 0 plus 1 equals to 1. This is equivalent to saying even numbers of 1 equals to 0 and odd numbers of 1 equals to 1. Now, let's look at an example of 5 and 7. First, let's convert 5 and 7 to its binary form, 100 and 111. The bitwise XOR addition of 100 and 111 is 011. 011 is 3 in decimal form. Therefore, the XOR addition of 5 and 7 is 3. Note, the calculation is associative and the order does not matter. Let us look at the previous example again. First, look at the left branch. We convert the nimbers of the two separate heaps, 1 and 4, to its binary numbers, 0 for both. Using what we have learned, we can use the XOR addition. 0 XOR 0 equals to 0. Therefore, the number of 1 plus 4 is 0. We can do the same for the right branch. 0 XOR 1 equals to 1. Therefore, the number of 2 plus 3 is 1. Using the max, we can calculate the number for the first game stage, which is the max of the numbers from the second game stage, which is max of 0 and 1 equals to 2. Therefore, the number of 5 equals to 2. This method can be used for game size of larger amounts.
Let's try to play the game together, you and me. Let's say I start first and have to split the heap of 7 chocolates. Notice that at game stage 1, I will be forced to make a move such that the number of the game position will be non-zero at game stage 2. Now it's your turn to make a move. Make a move such that you will go to a game position where the number is 0 in game stage 3. Yes, choose to split the heap into 1, 4 and 2 chocolates. Thereafter, I will be forced to make a move such that the number of the game position will be non-zero again in game stage 4 because I can now only split the heap into 2, 1, 3 and 1 chocolate heaps. Continue this method of playing and you will eventually reach the winning position.
In conclusion, the player should always try to go for a game position with a number of 0 so that the next player is forced to go to a non-zero position. Using this strategy, you will eventually land on the terminal position which has a number of 0, which is also the winning position. However, if you are the one to move from a game position of number 0 to a non-zero game position, good luck to you. You cannot do anything except pray hard that your opponent makes a mistake, and from then on, you play optimally until you are guaranteed a win. Assuming both players play optimally, the winner is already decided. So play smart. The winner depends on what the number of the first game stage is and who starts playing the game first. This table shows the numbers of the different initial heap sizes. From the table, we can see that the first block of heap sizes have a number of 0, while the next block has a pattern of 102, 102, whereas in the last block, the pattern is gone. From the diagram in the previous slide, we can tell that the numbers of the initial heap size do not have a periodic sequence. Therefore, we need access to a table of numbers for all game stages up to n-1 to find the number of the initial heap size. For instance, if we have an initial heap size of 7, we need to know the number values from 1 to 6 to solve the problem. To design an algorithm for this game with the winning strategy, we need the program to have an array of numbers corresponding to all the games with size smaller than the current game heap size. Then, the program would need to compute the number of the current game position using the previous numbers calculated, which is found in the array. This number is calculated using MEX. Interestingly, we have found that in Grundy's game, whether or not there is a particular game pattern of numbers for a list of n game stages remains as an unsolved problem, as it has been calculated by a mathematician named Akim Flamakam. For the first 2 to the power of 35 heap sizes, there has not been a periodic sequence found.
So, do you want to play a game?